Hello friends, today we're diving into the fascinating world of solar flares, powerful events from the depths of space that impact our planet. Are you ready to learn everything you need to know about these mighty solar events? Let's get started. Solar flares are massive bursts of energy, light, and high-speed particles that erupt from the sun. These flares are often associated with solar magnetic storms known as coronal mass ejections. The number of solar flares increases approximately every 11 years, and the sun is currently approaching another solar maximum, likely around 2013. This means more flares are on the way, some small and others large enough to send their radiation toward Earth. The largest solar flares, classified by their strength, are known as X-class flares. The smallest are A-class, followed by B, C, M, and X. Similar to the Richter scale for earthquakes, each letter represents a 10-fold increase in energy output. So, X is 10 times stronger than M and 100 times stronger than C. Within each letter class, there is a finer scale from 1 to 9. C-class and smaller flares are too weak to have noticeable effects on Earth. M-class flares can cause brief radio blackouts at the poles and small radiation storms that might pose a risk to astronauts. Then there are the X-class flares. Even though X is the last letter, there are flares more than 10 times stronger than an X1. The most powerful flare measured with modern instruments occurred in 2003 during the last solar maximum, and it was so intense it overloaded the sensors measuring it. These sensors maxed out at X28. The largest X-class flares are the biggest explosions in the solar system, and they are spectacular to watch. When the sun's magnetic fields cross over and reconnect, loops the size of many Earths leap off the sun's surface. During the largest events, this reconnection process can release energy equivalent to 1 billion hydrogen bombs. If directed toward Earth, such flares and associated CMEs can create long-lasting radiation storms capable of harming satellites, communication systems, and even ground-based technologies and power grids. CMEs are usually linked with sunspots and active region activities. Sudden changes in the sun's magnetic field cause plasma to be ejected from the corona and speed into space. When CMEs reach Earth, they can have significant effects on our magnetosphere, leading to radio communication disruptions, satellite malfunctions, and even auroras visible further from the poles than usual. The Carrington event of 1859 is one of the most significant examples of solar flares in history, clearly demonstrating the sun's impact on Earth. Richard Carrington, a British astronomer studying sunspots at the time, observed a sudden and intense flare on September 1, 1859. This flare occurred in the outer layers of the sun's atmosphere. While observing sunspots with specialized equipment, Carrington noticed a bright flash and energy emission. This flare sent a massive amount of energy and particles toward Earth, resulting in dramatic auroras that were visible far beyond the polar regions, creating an extraordinary display in the skies. A major blackout in Quebec in 1989 was caused by the interaction of solar particles with Earth's magnetic field. On March 13, 1989, a strong solar flare sent charged particles rushing toward Earth. These particles usually get deflected by Earth's magnetic field, but the sheer volume and energy of the 1989 particles overwhelmed this shield. This interaction led to chemical reactions in the upper atmosphere at high latitudes and significant impacts on Quebec's power transmission lines and transformers, resulting in a widespread blackout. The 1989 Quebec blackout is a key example of how solar activity can impact Earth. Solar flares and solar radiation events in the 2000s had significant impacts on space communication systems and satellite technology. To minimize or prevent these effects, space agencies and satellite operators typically employ various strategies to protect satellite systems from solar radiation. These strategies include using radiation-resistant materials, creating backup systems, and utilizing space weather forecasts. One of the largest solar storms ever recorded occurred in July 2012, during the peak of the solar cycle. This event saw a massive coronal mass ejection that expelled a huge amount of plasma and magnetic field into space. Had this ejection directly targeted Earth, it could have had serious consequences. Although Earth was not directly hit by the 2012 event, if it had been, satellite communication, GPS systems, and power grids could have been severely impacted. In 2021, the Sun entered its 25th solar cycle, during which solar activity is expected to increase. The solar cycle refers to the roughly 11-year period over which the Sun's magnetic activity changes, causing fluctuations in various activities on the Sun's surface and atmosphere. One of the most noticeable indicators of the solar cycle is the change in the number of sunspots, which are cooler, darker areas on the Sun's surface. The number of sunspots increases at the solar cycle's maximum and decreases at its minimum. Sunspots form where the Sun's magnetic field emerges onto the surface and are regions of strong magnetic activity. May 2024 has proven to be an especially stormy month for our Sun. In the first week of May, a barrage of large solar flares and coronal mass ejections, CMEs, sent clouds of charged particles and magnetic fields hurtling towards Earth, resulting in the strongest solar storm to hit Earth in 2 decades, and possibly one of the strongest ever, said Teresa Neves Chinchilla, acting director of NASA's Moon to Mars Space Weather Analysis Office. The first signs of the solar storm appeared late on May 7th with 2 powerful solar flares.
We will study this event for years to come, and it will help us test the limits of our models and better understand solar storms.
From May 7 to 11, numerous strong solar flares and at least 7 CMEs headed toward Earth. Among these flares, 8 were X-class, the most powerful type, with the strongest peaking at X5.8. Since then, the same solar region has produced even larger flares, including an X8.7 flare on May 14th, the strongest seen in this solar cycle. The CMEs, traveling at speeds of up to 3 million miles per hour, began arriving at Earth in waves starting on May 10th, creating a prolonged geomagnetic storm that reached G5, the highest level on the geomagnetic storm scale, a level not seen since 2003. The CMEs all arrived largely at once, and conditions were just right to create a truly historic storm, said Elizabeth McDonald, NASA's heliophysics citizen science lead and space scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. When the storm reached Earth, it created brilliant auroras seen worldwide. The auroras were visible at unusually low latitudes, including as far south as the southern US and northern India. The most intense auroras were seen on the night of May 10th and continued to light up the night sky throughout the weekend. Thousands of reports submitted to the NASA-funded citizen science site Aurorasaurus are helping scientists study the event and learn more about auroras. Cameras, even standard smartphone cameras, are much more sensitive to the colors of auroras than they used to be, McDonald said. We have a great opportunity to learn more about auroras through citizen science by collecting photos from around the world. According to a measure of geomagnetic storm strength known as the Disturbed Storm Time Index, which dates back to 1957, this storm is comparable to the historic storms of 1958 and 2003. With reports of auroras visible at magnetic latitudes as low as 26 degrees, this recent storm may rival some of the lowest latitude aurora observations recorded in the last 5 centuries, though scientists are still evaluating this ranking. Measuring storms over time is a bit tricky because our technology is constantly changing, said Dolores Knipp, research professor at the Smead Aerospace Engineering Sciences Department and senior research associate at the High Altitude Observatory of the National Center for Atmospheric Research in Boulder, Colorado. Aurora visibility isn't a perfect measure, but it allows us to make comparisons across centuries. McDonald encourages people to continue submitting aurora reports to aurorasaurus.org, noting that even sightings of no auroras are valuable in helping scientists understand the event's scope. Before the storm, the Space Weather Prediction Center of the National Oceanic and Atmospheric Administration, responsible for predicting the effects of solar storms, sent notifications to power grid and commercial satellite operators to help mitigate potential impacts. These warnings helped many NASA missions prepare for the storm. Some spacecraft proactively shut down certain instruments or systems to avoid problems. NASA's ICESat-2, studying polar ice sheets, entered safe mode, likely due to increased drag from the storm. Better data on how solar events affect Earth's upper atmosphere is crucial for understanding the impact of space weather on satellites, crewed missions, and Earth and space-based infrastructure. So far, only a few limited direct measurements are available in this region, but more are coming. Future missions like NASA's Geospace Dynamics constellation and the Dynamical Neutral Atmosphere-Ionosphere coupling will be able to observe and measure how Earth's atmosphere responds to energy flows during solar storms like this one. These measurements will also be valuable as NASA sends astronauts to the Moon and later to Mars with the Artemis missions. The solar region responsible for the recent storm has now rotated to the far side of the Sun, where its effects can no longer reach Earth. However, this doesn't mean the storm is over. NASA's Solar Terrestrial Relations Observatory, currently orbiting about 12 degrees ahead of Earth, will continue to monitor the active region for another day after it becomes invisible from Earth. The active region is just beginning to come into view from Mars' perspective, said Jamie Favors, director of NASA's Space Weather Program at NASA headquarters in Washington. We're starting to gather some data from Mars, so this story is far from over. These events are closely monitored by space agencies and researchers. NASA, ESA, and other international space agencies continuously observe and study solar activities. These efforts focus on predicting solar flares and developing space weather forecasting models. To learn more about solar flares, follow the reports, websites, and scientific papers published by space agencies and researchers. These sources help us better understand the dynamic nature of the Sun and the effects of solar flares on space and Earth. Today, we've journeyed into the mysterious and fascinating world of solar flares. If you enjoyed our video, be sure to hit the like button and subscribe to our channel. See you in the next video. Take care and stay curious.